Let's go over the functional programming question I did yesterday. So I think it's a pretty standard question of basically using the fold and fold fusion, and then also testing a bit on trees and folding on that. So I'm going to start off with the first part. Standard function sum and map might be defined recursively by, okay, this, and the map is this. For part A, prove that this thing is equal to that thing for all finite list AS. So basically for this part, what we're asked to do is sum of map times x AS equals sum of AS times x. So that essentially, if we were to do this out by hand, then what this would mean is um, first doing something map of each one. So if the element of this was A1 times x plus A2 times x all the way to AN times x. This would be the left-hand side and it would sum it together, right? So the right-hand side would just be the sum of the things, which would be A1 plus A2 plus all the way to AN, and then all this times x. So basically what this is asking me to do is just prove the distributivity thing property. So I can't just show it like this, obviously. I would have to show it as using proof by induction. So how that's gonna go is we have something like this. We have the thing we want to prove. We're gonna first test the base case, right? On the left-hand side, when AS is equal to an empty list, we have the sum of map of this. Map of an empty list would just be the empty list. Sum of an empty list would be 0, so the left-hand side is equal to 0. On the right-hand side, sum of the empty lists would be 0, and 0 times x would just be 0, so it's also 0. So 0 equals 0, we're done with the base. Next, we're moving on to the inductive step. So our hypothesis is that this property holds. So we want to show that it holds for A cons AS. So then it's the next one, right? Um, so then this would just be the property we want to show. On the left-hand side, what we have is we have the sum of this thing. So what we can do is by the definition of map, we can just map x times x to a. So we have ax, and then we have the cons and then the remainder of the map, right? And then the definition of sum is that we can move ax outside of the sum and it would just be ax plus this. And by our induction hypothesis over here, this would just be um, the sum of AS times x, right? Just using inductive hypothesis over here. And then on the right-hand side, we have this. So by definition of sum, we can just extract it out, right? To be A plus sum AS. This is just what we have. We just extract this part out. Next, what we do is we just times x to that by distributivity. We have AX plus this. And we're in the same form where the left-hand side equals the right-hand side. So we're done. Okay, moving on for part B, we want to prove that this holds for all infinite lists AS. So for proving that it's true for infinite lists, we just want to prove that um prove the case for bottom, right? Because infinite is bottom. So on the left-hand side, what we have is we're going to be calling map and sum. So it would always continue because it never reaches the base case. So the program hangs so that we get infinite. And then on the right-hand side, we are calling the sum and evaluates to bottom. So hence bottom times x would just still be bottom. So bottom equals bottom and hence is true for infinite. And then part C, we're asked to show the fold fusion law for fold R on list is that this holds, right? F fold R GA is equal to fold R H of B, provided these three conditions. Give a brief outline of the proof of the fold fusion law with sufficient detail to account for the three conditions. Okay, so for this part we have, okay, this was what we have, right? And we're just going to do structural induction on x's. If x's was a bottom, then what our left-hand side would be f of fold R bottom would just be f of bottom because fold of anything would just be bottom, right? And then that means that because on the right hand side we have fold of HB of bottom is equal to bottom, so F of bottom has to be bottom, right? So that's condition one. And it's true. For the second part, if X's was a list, empty list, then the left-hand side would be this thing, which the fold of this would just by definition be A, so it would be F of A. And the right-hand side would be fold of this empty list, which would just be B. So then our condition two would just be FA is equal to B. And then for the third condition, we kind of just assume, okay, our x's is y, cons y's, so then we have two elements to it, right? Like the first element and the remainder of the list. So we're just gonna assume that like our induction hypothesis is that this holds, right? And now we're just gonna call Z to be fold R of GAYs. So then on the left-hand side, we have this thing, right? And by definition of fold, what we can do is we can apply it to G of Y in the front and then the remainder of the fold. And then we see that because we defined Z conveniently to be this, we're just going to replace this by Z so that it seems a bit shorter. And on the right-hand side, we have this thing over here. This thing is just basically, we can apply the definition of fold as well to the first part. So we have HY and then fold R, the remainder. And then we can further kind of use the um, definition of like our induction hypothesis to kind of write this thing as the f of fold R of G of A Y's. So then we can rewrite this as the inner part would just be Z, so then we just have HYFC. So condition 3 would just be a f of GYZ is equal to HYFC. So written in point form, it would just be f composed of gy is equal to hy composed of f. So we have shown the conditions. In part D, we're asked, without any further recourse to induction, prove that sum and map functions defined above can be written as folds, and use fold fusion twice to show that this property holds, right? So I think this is getting a lot neater because before we had to kind of spam it out with induction to show that's true. Here we're going to use fold fusion, which is pretty neat to show that it's actually the same by fusing both sides. Okay, so we have the basic functions, right? Sum and the map f. So we want to write these in terms of fold, right? So these are pretty standard bookwork. So this is fold R plus and then 0. This would be fold R of y, y's, fy cons y's of an empty list. I think this is just mainly taking the definition of what was written over here, like the recursive definition, and writing up the fold for that. And what we do is we want to show that this holds, right? So to show that this holds, this is basically written in point form, like the more concise form. So we want to show, okay, yeah, we're going to apply fold fusion. So on the left-hand side, if we're going to fuse this, we have um, the function, which is x times x, right? And then our main thing, which is sum. So then our f would just be times x, and then our sum written up would be fold r plus 0. So then our g would be plus, our a would be 0. And then we check the three condition, right? Times x is strict, b equals fa, so fa would just be times 0, which would be 0. And then our third condition is fgyz is equal to hyfc. So then we just plug in what we have into this equation, and then on the left-hand side, we have times x, y plus z. So then it would just be x times y plus z. So then it would just be xy plus xz. And on the right-hand side, we have hy, z times x, right? So then h would just be, we're just trying to find what h is. So h would just be taking y and z prime, and it would just do y times x plus z prime. So z prime is just our accumulator, and then we're just times y to x, and then plus that to the accumulator. So that's our function h. So our final fold fusion kind of equation would just be our fold our HB, which our H is this, B is that. Okay, for the right hand side, we did the exact same thing, but just writing it as our F is sum and then fold our G, A. G is this, A is that, right? And then we again check the conditions. First one is sum is strict because F, yeah, F equals sum, right? Next is B equals FA. FA is equal to 0 as well. FGYZ is equal to HYFC. So then we plug F as sum and then G is this thing, and then YZ is equal to HY sum Z. So then we do because we already have the two parameters y, z, right? We just put it back inside here, and it would just be xy cons z, um, x times y cons z. And then on the right hand side, we have this, right? And then on the left hand side, we can further kind of extract xy out of the sum by just doing that, and then just be sum z. So we basically have our h function would just be taking uh, y and z prime as parameters, and then doing y times x plus z prime, right? So then we would get the same thing after the fold fusion. So since the two sides are equal, hence it's equal. I think it's pretty neat to do it the fold fusion way because it shows algebraically that it's the same rather than just doing it inductively. Okay, then we're kind of moving on to the data types, just not only on lists, but actually on a new data type called rows trees. So we have this definition of the data is a tree A, and it has kind of two constructors, one A and many tree A. So for part E, we're asked to write a recursive definition for the fold function. This thing over here for the tree type. So we see that, okay, yeah, we have kind of three parts. I mean, two parts to it, I'd say. This one is the first part, A to B. This one is just our first one when we deal with one, right? And then this one would be the second one, which would be the case when we have many. And then this is our input, like this is our input tree A, and then our output is a B. So I'd say, yeah, this one's one. However many constructors we have, however many functions we have here that we deal with. And then we have always our input and then we have our output. So that's kind of how we kind of fold up a data type is we construct it using these, we destruct it using the same thing, right? Like we combine it together or we create it. So that's the idea. So how we're gonna write up this fold is just taking advantage of the thing, right? So we're just gonna write the first function, which is called one, and then the second function, which is called many, and then we just kind of pattern match it. If we have the 1x, we're just gonna apply the function 1x. And if we have many, then we and our input is many ts, then we would have to kind of process it one by one, right? Because we can't just straight call the function many because many expects the type of all a list of results of B, but we're inputting trees, right? Which is not the thing we want. So we first have to map and apply this fold to all of the subtrees, right? And then once we get that, then we can call and combine all of the things together using our function many. So that's the idea, is that we can't, because of the type that we see, this is a list of bees, and we're right now dealing with many, then we have to first use a map and make sure that we get it to the right type, and then combine it together using the function. Okay, for part F, I think this one is the hardest of this chapter, but I think it's the neatest because it really shows how kind of fold and fold fusion can be applied to many data types. So we kind of have this fold fusion law of F fold T one many is equal to fold T PQ, provided that these are the three conditions. Okay, I'm gonna first show that this is true, right? Before I move on to the next part. But in a real exam, probably, yeah, just continue on. But yeah, I would first show that this kind of fold fusion law holds, right, for the three conditions. Because this fold T, how would we actually kind of work around this, right? This is what I did. Why are the three conditions true, right? So for the first condition, if we have such a fold, right, the idea behind fusion is that we always have some kind of function here, and then we have our fold of the original thing, right? So fold of one many. And ideally, we don't want this f. We just want to combine it so that we just have something of p and q, right? That would be like the convenient form. So that's why how we got this original fold fusion equation. So then we're going to find the three conditions, right? If t was bottom, then our left-hand side would be f fold t, one many bottom. So then that would evaluate to f bottom, right? And the right-hand side, f fold of something bottom would be bottom. So f bottom is equal to bottom, so f is strict. So this is exactly the same as the one for less, but just applied over here. The second one is the proof for the second condition. We're going to just set the minimum case, so t equals 1x. So on the left-hand side, we would have this equation where we have 1x, and then because we define the fold to be that way, right? If we apply to 1x, we're just going to call the function 1 on x, right? So it would just be f of 1x. On the right-hand side, we have this, right? So we know that our fold, we have defined it to be just calling the first function when we deal with the 1, right? So it would just be px. So we know that f1x is equal to px. If we write it in point form, then it would just be f composed of 1 would just be equal to p. So that would be what we have. And then the third condition is the most complicated of the bunch, but I guess it's also the same for list, right? Because it's kind of the one that requires more steps. So on the left-hand side, if we were in the case of many TS, right? Before it was for list it would have been x cones x's, but here it would be many TS. So here what we have is on the left-hand side, we would have f of and then we have this fold one many many. But we already know that if we're writing this fold, then we would just call the many function, right? Many of the map of fold of one many TS. So that would just be the case. And then because it's quite long, we're just going to call this expression map fold OM TS M, capital M, just for the sake of it. So on the left-hand side, we have F many M. On the right-hand side, we can do something like this. We know that we have fold PQ many, right? So we're gonna call them thing. So we're gonna call Q, right? So before it would be Q and then it would be map fold PQ of TS. So by induction hypothesis, uh, for lists, we would just call like the case for x's, right? We just write it in the same form as x's and then use the induction hypothesis. Here, our induction hypothesis would be that it holds for smaller children in TS, right? So, what that means would be in this smaller fold over here, this fold PQ, it would just be F fold one many, right? Because it would just be using what we have above. Where is it? Can't seem to find it. But the idea, you get the idea. The idea is that in our law, like we would just use, where am I? Yeah, basically fold PQ is equal to F fold of one many, right? So then this would just be the induction hypothesis because this is applied to a subtree, right? So then hence we would get this over here instead. And then we're going to use the map law, but the opposite way. So we're going to split one map into two because if you map one thing and then map the other thing, you map two things and you could have done map one thing and then map the next, right? So instead what we're going to do is Q and then we're going to map F first, right? So then we extract. I'm going to do it in this color. So we have this, right? We're going to first do map F and then we're going to map the remainder, which was map fold one many TS. So this would be the second. And we see that this later part would just be M, right, that we defined earlier over here. This is the exact same thing. So hence what we can do is we can write it as Q map F of it. So we want to show that the left-hand side equals the right-hand side, so we're going to equate it together, those two things. So then in point form, we're going to do F many equals Q map F. So this would be the condition 3 that we have. Okay, so now that we proved kind of how the fold fusion works and why those three conditions are the way they are, we can kind of move on to part F, right? Write as instances fold T, definitions of functions sum T and map T. So sum T is of this type, map T is of that type. It makes sense because if we have something, right, we're gonna input a tree and we're gonna want to get out a value. And then for map, we're gonna input something of type A and then get out type B. Basically, we're gonna input a tree A and then we're gonna get a tree B. So we're gonna process that, right? And then we want to prove that the same statement from before holds for trees as well. Okay, so the idea would be exactly the same. Use the fold fusion on the left-hand side, use the fold fusion on the right-hand side for trees, and then show that those two are the same. So that would be kind of our approach. Okay, so we have this. This is sort of like the conditions that I just copied down from earlier. I can write that sum of t is equal to fold t identity sum because for sum, if it was just one, right, it would just be itself. We don't even need to sum it up. It's just that thing. If it was multiple items, then we just have the sum of those things, right? For map of t, what we have is faux t, and then we would want first to apply the function, right? But the function gets out of the type of just the thing. But we want it to be back to the tree form because that's kind of what we need at the output, right? So we're going to have to do compose it and get it back to the leaf form of the tree. So then we're going to do one. And then we obviously have this in the case of the many, we would just call them many. So that's the idea is that for the map, what we have is we want to consider the types, right? Because for the one case, we would just apply F to it. If it was just one value, we'd apply the F to it, so that it would become a value. But we need a tree to be outputted, so then we need to get it back to the leaf form. So we're going to call one. And for the many, because calling it the many won't would just get it done and get it back to a tree, we're good. So that's kind of how we have. So we want to prove that this statement holds, so we're going to write it in point form, which is nicer, and I'm going to apply our fusion. On the left-hand side, we have f is equal to sum t, and then fold our one many, where our one is this function, many is our capital many. So for condition one, we're going to check what f is, right? F is sum t and it's strict. For the second condition, we want to check the p, right? P sum dot composed of one. So then our one function here would just be the one composed of I mean times x. So then we would have this. And we know that if we were to do the sum of one, then it would just be the identity. So hence we have identity times x, which would just be identity like the times x. So hence p is equal to times x. Sum and one, sum composed of one. That one is identity because if we were to think about it, like if we were to have a leaf of a value, each of the leaf sums it up together, we just get that thing back, right? Because we just have one element to that. So there's not much to say. Um, third condition, F composed of many is equal to Q composed map F. So we have sum T composed of many is equal to Q map sum T. So we get that Q is equal to sum. Because if we have the sum of many, right, that gives us the whole thing. So that if we were to just apply the sum of each one, then we would have to sum everything up to get the final sum, right? So that's why our Q is sum. So then we get our left-hand side fusion would just be fold t times x of sum. And on our right-hand side, when we apply the fusion, we would set up it to be this way. We would have f is equal to times x, and then our one function would be identity, our many would be sum. So then for the first condition, we check f is strict, so times x is strict, that's true. For the second condition, we want to find p is equal to f composed of 1, which would be times x, and then 1, which would be identity, so it would just be times x. Third condition, f composed of many is equal to q composed of map f. So when we plug this in, we get this. Again, we see the same situation, right? If we have many and then we're timesing x, we just get the whole thing, right? Whereas the other one, if we have the map, we already times it together, so we're just trying to find the sum. So hence we get the same equation from the fusion. So the left-hand side equals the right-hand side, and we're done our proof. So overall, I'd say the difficult part in this question, I think this question was fairly doable, I'd say. It's pretty standardized, and it definitely shows that how powerful fold can be for both lists and also for other data types that we define. So yeah, end it off here.